Welcome to another video in vector calculus. Today's topic is all about the divergence theorem. I will start out by giving a motivating example on why we might care. And then what I'll do is I'll state the divergence theorem. It's a really important theorem and it's helpful, as the motivating example will show. I'll give a partial proof. The full proof is quite long, so instead I'm just going to give a proof for one of the variables and in a special case with a special kind of surface. And then I'll show some examples on how the divergence theorem is used and also how to verify that the divergence theorem works. And then finally, we're going to look at the divergence theorem and try to understand how that helps us learn about the divergence of a vector field at a point. So let's start out with this example. So the question is to find the double integral over a surface of f dot n ds. This is also called a flux integral. So what is the flux through the surface with this vector field f? Where f of xyz is quite messy. In fact, it's so long and messy, I won't even read it out because it'll take too long. Instead, just note this is a really ugly vector field. The surface itself doesn't look too bad at first glance because it's just the unit cube. And the unit cube, look how friendly it is until you delve deeper and realize what you're going to have to do. The unit cube has 6 different sides. So that means each of these sides has a distinct unit normal vector. And because of that, we're going to have to do 6 different double integrals, each of them involving this really long and awful vector field. I do not want to do this particular flux integral. But fortunately, we are going to have the divergence theorem come to our rescue. So let's state the divergence theorem. And it says, let S be the boundary of a solid region Q with outward pointing unit normal vector, n. And let capital F be a differentiable vector field with continuous partial derivatives. Then we can say the following. The flux integral, so the surface integral over the surface S of f dot n ds is equal to the triple integral over the solid Q of the divergence of f dv. And remember, the divergence of f was the sum of the partial derivatives of f with respect to x, y, and z for each component respectively. We'll have plenty of examples today. So now we can get back to this seemingly awful example where we wanted to find out what the flux is of this vector field on the cube. So this is so much better with the divergence theorem. So first, let's find the divergence of this vector field. Notice that the component of I, that's y e to the z squared cosine of 4y, doesn't have any x's in it. So the partial derivative of the first component of f with respect to x is just 0. Similarly, if we look at the second component of this vector field f, it doesn't have any y's in it. We can also conclude that the partial derivative of the second component of f with respect to y is 0. The third component, it does have a z, but it's just z plus some messy function of x and y. And I can very easily take a partial derivative of the third component of f with respect to z, and I just get 1. So in particular, the divergence of f will be 0 plus 0 plus 1. When I want to find out what the triple integral over the solid is of the divergence of f dv, the divergence of f is very beautiful. It's just 1. And the solid actually is very nice also. If you're looking at a surface integral, a cube is terrible because it has 6 sides. On the other hand, if you're looking at the cube as a solid, the cube is beautiful. And the limits of integration will just be 0 to 1 for each of the 3 limits because we have a cube. So what we can say from the divergence theorem is that this flux integral, the double integral over the surface S of f dot n ds, is equal to the triple integral from 0 to 1, 0 to 1, 0 to 1 of 0 plus 0 plus 1 dv. I could do that integral in my sleep, because that's just the volume of the unit cube, because whenever you're triple integrating 1 dv, that's just the volume. And the volume of the unit cube is 1. And that's all there is to it. So the divergence theorem allowed us to calculate this flux integral, which seems really horrible, but do it in such a way that it's one of the easiest triple integrals imaginable. And we just get 1. So the next step is to say, why does the divergence theorem work? Let me give you a partial proof. Let me remind you that the left-hand side of the divergence theorem is the surface integral over S of f dot n ds, and we can think of f in differential form. That's mi plus nj plus pk. It's a little bit awkward because when we write it in differential form, this n, the nj, is different than the unit normal vector, even though we use the same letter. But because I'm not going to focus on that, it won't matter. We'll be all right. So we could say that the surface integral of f dot n ds is equal to the surface integral over S of mi dot n plus nj dot n plus pk dot n ds. And I will focus just on this third term, pk dot n. The other terms are similar, it's just more work. And what we want to show is that this particular surface integral is supposed to be equal to the triple integral of the divergence of f dv. But the divergence of f is a sum of the partial derivatives of each of the components. So we get m sub x plus n sub y plus p sub z dv. So as I mentioned, my focus for this partial proof, not a full proof, is to show that the surface integral of just the pk dot n part ds is equal to the triple integral over q of just the pz dv. It's a very interesting property of the divergence theorem is that it's actually a little bit more than what it says. Not only does the full surface integral equal to the full triple integral, each of the components equal each of the components. So I'm going to look at the z component, or the third component of each side. And I'm going to make one further simplification to make life a lot easier. And that is, I'm going to assume that this surface S is bounded below by a function g1 of xy and above by a function g2 of xy. Often that's the case, but if it isn't, there are tricks we can do to make it still work. My goal is going to be to work out the left-hand side get something from it, and then work out the right-hand side, get something from it, and then notice that what we got from each of the sides was the same. So let's start out with the left-hand side. So I will work out the flux integral, so the surface integral of pk dot n ds. So because this particular surface has a top and a bottom, we have to calculate the flux integral by calculating the tops and bottoms individually and adding up the two fluxes. So let's start with the top. So the top integrand is pk dot n ds. So that is pk dot, and now let's look at n. So if we're looking at the top, that is the z equals g2 of xy. And because it's the top, the normal vector is pointing upwards, because when we're talking about a positively oriented surface, we're always talking about it pointing outwards from the surface. And when you're on the top, outwards means upwards. So remember, when we had the upward component, we let the z component of the normal vector be 1. And then the x and y components will be negative the respective partial derivatives. So in particular, the unit normal vector that is positively oriented or oriented upward will be negative the partial derivative of g2 with respect to x, I, plus negative the partial derivative of g2 with respect to y, j, plus k. If we work this out, it's very easy, because whenever you take pk dot a big vector, that just says take p times the k component of that vector. The k component is 1, so we just get p. I'm going to write it longhand, because p is a function of 3 variables, x, y, and z, but z for this surface is g2 of xy. So we can say that the integrand for the top is p of xy, g2 of xy. Now let's work on the bottom. So the bottom, same idea, except now when we're talking about the unit normal vector, since it points outwards, that's downwards on this bottom area. Because it's downwards, I have a negative k, and we have positive first derivatives. So we could say that pk dot n ds is equal to pk dot g1 sub x, I, plus g1 sub y, j, minus k. And then I take the dot product, again, because we have just a pk, we're just dotting it with this minus k, and I get negative p of x comma y, comma, and since we're in the bottom part, where z is equal to g1 of xy, we can write g1 of xy. So now we have the top and the bottom. And because they intersect in the same intersection, the region of intersection is the same. So we could say that the surface integral over S of pk dot n ds is equal to the double integral over the region of intersection of p of xy, g2 of xy, minus p of xy, g1 of xy, dA. So keep that in mind, because that is one way of writing the flux integral. What I want to do now is I want to find out what is the triple integral over the solid Q of the partial derivative of p with respect to z dv. So let's work that out. So we could say that the triple integral over q of the partial derivative of p with respect to z dv is equal to the double integral over r of the single integral from bottom to top, remember the bottom was g1 of xy, the top was g2 of xy, of p sub z dz times dA. So that's just realizing that the triple integral is the double integral of the single integral. But now there's something really nice. We have this p sub z dz. What is the integral of the derivative? And that's itself. So the integral of p sub z dz is just p. So I could rewrite this triple integral now as a double integral over the region R of p from g1 of xy to g2 of xy dA. Now I can plug in, and I can say that this is a double integral over R of p of xy g2 of xy, that's plugging in the upper bound, minus p of xy g1 of xy, that's plugging in the lower bound, dA. And lo and behold, that's the same as the flux integral. And that proves, at least partially, that part of the divergence theorem. So now let's use the divergence theorem. So here's an example. Let's find the surface integral over the surface S of yi plus y squared zj plus xk dot n ds, where S is the first octant part of the sphere of radius 5, centered at the origin, along with the quarter disks of intersection. So the good news is we can use the divergence theorem, since S is a closed surface, and certainly the vector field is differentiable. The partial derivative of the first component with respect to x is just 0. The partial derivative of the second component, y squared z, with respect to y is 2yz. And the partial derivative of the third component, x, with respect to z, is just 0. So the divergence will be 0 plus 2yz plus 0. So the divergence theorem tells us that this flux integral is equal to the triple integral over the solid Q of 2yz dv. So now let's work this out. Notice that since the surface is a sphere, that tells us spherical coordinates will probably be the best way to work this out. I do it that way. I have my 2. Y is equal to rho sine theta sine phi. Z is equal to rho cosine phi. The Jacobian, when we transform into spherical coordinates, is rho squared sine of phi. We have a d rho, d theta, d phi. We're talking about the first octant part of a sphere of radius 5 centered at the origin. So rho goes from 0 to 5, since the radius is 5. We're only in the first octant, so phi goes from 0 to pi over 2. And theta also goes from 0 to pi over 2. That keeps it in the first octant. This integral actually is not that difficult. In fact, if you look at the rho component, we have a rho times a rho times a rho squared. That's a rho to the 4th. The integral of rho to the 4th is rho to the 5th over 5. If you plug in 5, you get 625. The integral of sine of theta is just negative cosine theta. If we plug in 0 and pi over 2, that just gives us 1. And for the integral of sine squared of phi times the cosine of phi, we can just use a u substitution with u equal sine of phi, du equals cosine of phi d phi. We end up with a u squared. The integral of u squared is u cubed over 3. So that tells us that the integral of the sine squared phi times cosine of phi is just sine cubed of phi over 3. And if you plug in pi over 2 and 0, you just get a third for that. So if you put all that together, Or, by the way, if you're allowed, you can use a calculator to do what I just did. You end up getting 1,250 divided by 3. If you tried to do this without the use of the divergence theorem, it would be much more difficult. First thing is you'd have the sphere, you'd have to get the unit normal vector for the sphere, take a dot product. Then we'd have to do, remember, the quarter discs of intersection along the xy plane, the yz plane, and the xz plane. There'd be 4 different integrals to work out. It would be messy, but I don't want to do that because I can use the divergence theorem. Often, when we're thinking about the divergence theorem, we want to make sure it works. The question I have is, let's verify the divergence theorem for a specific example. So we want to verify that the flux integral, the surface integral over S of f dot n ds, is equal to the triple integral over q of the divergence of f dv. Where f is the vector field, 2z, 3y, 4x, and q is bounded above by the plane 2x plus 2y plus z equals 2, and below by the paraboloid z equals x squared plus y squared. The bad news about this is that this is at least twice as hard as just the last example where we had to use the divergence theorem. Because if we want to verify the divergence theorem, we have to compute the left-hand side of the divergence theorem, we have to compute the right-hand side of the divergence theorem, and then we have to notice that the two answers are equal. The first thing we should probably do is look at a picture. It's bounded above by this plane here, and it's bounded below by this paraboloid here. And you get this interesting shape. Now what I need to do is I need to verify. So I'm going to start out with the left-hand side, find out what I get, and then I'll work out the right-hand side, cross my fingers, and hope I get the same answer. Let's start out by finding the unit normal vectors for each of these two surfaces. Because when we're talking about the surface integral, there's two pieces. There's the planar region, and then there is the paraboloid. First, for the region on the paraboloid, that's the bottom piece, and the normal vector points downward. In particular, we can let the k component be -1. The I and j component will be the partial derivatives with respect to x and with respect to y, respectively. The partial derivative of x squared plus y squared with respect to x is 2x. The partial derivative of x squared plus y squared with respect to y is 2y. Our normal vector on this bottom surface is 2x, 2y, -1. For the top surface, it helps if I solve for z and say that z is 2 minus 2x minus 2y. Notice that for the top surface it points upwards, so I will let my k component be 1, and I'm going to take the negative of the partial derivatives with respect to x and y. So remember, we have z equals 2 minus 2x minus 2y. The partial derivative of z with respect to x is -2. -2 is +2. The partial derivative with respect to y of 2 minus 2x minus 2y is also -2, and -2 times -1 is 2. So that tells us the second normal vector corresponding to the planar part is 2, 2, 1. Because we're going to integrate this over the region, and it's really the region of intersection, I need to find the intersection. So if I substitute x squared plus y squared for z in this first equation, 2x plus 2y plus z equals 2, and then I do some algebra magic, I'm going to complete the square, then I end up with x plus 1 squared plus y plus 1 squared equals 4. And that is a circle of radius 2, centered at the point -1, -1. So my little man, and my cat will verify, my little man has the feet down at the bottom, and we have to solve for y to find out what this bottom curve is. We can say that y is -1 minus the square root of 4 minus x plus 1 squared, and that's where the feet stand. And the head is bounded by -1 plus the square root of 4 minus x plus 1 quantity squared. The farthest the little man can get to the left is -3, and the farthest the little man can get to the right is +1. So that's going to help us find our bounds. But we also need to find the f dot n ds piece. So do that. Let's start with n1. We need to take f dot n, or f is 2z, 3y, 4x. If we dot it with our n1, we get 4xz. But remember, z is x squared plus y squared for this n1, the bottom surface. So we get 4x times x squared plus y squared. The second component gives us a 3y times 2y, which is 6y squared. There's our 6y squared. The third component gives 4x times -1, so we have a minus 4x. For the second part, we can take f dot n2. So now we're talking about 2z times 2, which is 4z. But remember, now we're talking about the planar region where z is 2 minus 2x minus 2y. We get 4 times 2 minus 2x minus 2y. Then we have a 3y times 2 is plus 6y. Then we have a 4x times 1 is plus 4x, all dA. So we could put that together, all of what we've done. We have, remember, the little man went left to -3, right to 1. And the little man's feet were at -1 minus the square root of 4 minus x plus 1 quantity squared. And the little man's head was at -1 plus the square root of 4 minus x plus 1 quantity squared. And then I can multiply this out and combine like terms and get 4x cubed plus 4xy squared plus 6y squared plus 8 minus 8x minus 2y dy dx. This one is not that easy to figure out. I actually, to be honest, I used a computer, and what I ended up with was about 75.4. And that's what the computer gave me for the left-hand side of the divergence theorem, the flux integral, the double integral over the surface S of f dot n ds. We're halfway there. Now we have to find the triple integral over the solid of the divergence of f dv. Turns out that's a little bit easier. But let's work that out. I need to first find the divergence of f. If f is 2z, 3y, 4x, the partial derivative of 2z with respect to x is 0. The partial derivative of 3y with respect to y is 3. And the partial derivative of 4x with respect to z is 0. So the divergence of f is 0 plus 3 plus 0, which is just 3. Now I can find the integral. I can write this as a triple integral. The first two sets of bounds are the same as what we have before, -3 to 1. -1 minus root 4 minus x plus 1 quantity squared to -1 plus the square root of 4 minus quantity x plus 1 squared. And then the inner limits. That's going to be the top and bottom surfaces. The bottom surface is z equals x squared plus y squared. So x squared plus y squared is the lower limit. The top surface can be written as 2 minus 2x minus 2y. That gives us the upper limit as 2 minus 2x minus 2y. And then the integrand is the divergence of f, which was just 3 dz dy dx. This also is a pretty miserable integral. I actually used technology. I used a computer. And what I got was that this triple integral is about equal to 75.4. And that agrees with what we got for the left-hand side. So we have verified the divergence theorem for this example. I have one last thing to talk about. At the beginning of this chapter, we looked at the divergence at a point, which was just the sum of the three partial derivatives. We just computed it, but now we can actually understand it if we think about the divergence theorem. The divergence theorem is that the flux is equal to the surface integral over the surface S of f dot n ds, and that's equal to the triple integral over the solid Q of the divergence of f dv. So now comes a little thought. If we want to find out what the divergence is at a point, we can approximate that by saying, what about if we take a little tiny ball around that point? And if you do that, then the vector field will be approximately constant, which means the divergence of f will be approximately constant. And when we have the triple integral over a solid of a constant times dv, that gives us the divergence of f, that constant, times the volume of the solid. What I could do next is I could just divide by the volume of Q on both sides. And what I can say is that the divergence of F is about equal to the flux per unit volume. So I like to think about the surface as a net in the water, in a lake, and there's fish trying to get out. And the question is how fast you catch and fish. But there also might be fish coming in to free other fish. Every time one comes in, you get a freedom. Every time you get out, then catch one. So the divergence of F is kind of the net gain of fish in a little tiny net around that point. That's one way of looking at it. So here's an example. Here is at least a cross-section, a two-dimensional cross-section of a vector field. And notice that from the center, all of the arrows are going outwards. So this is emanating vectors from that point. We often call that point a source because it's a source of vectors coming out from it. In physics, sources are typically things like the sun because light's coming out or energy's coming out. So that gives us a source. Electron could be a source of electromagnetism, for example. You get an electrical field around an electron. There's all kinds of sources that happen in physics. And because we have a source where things are emanating from the point, the divergence of F is positive because the flux per unit volume is positive. We're getting a net gain onto that net. You could also look at the exact opposite. Here's another vector field, and we can see that all of the vectors are going in to that point. So instead of calling it a source, the technical word is a sink. It's not a very hard word at all, but that's what everyone uses. Because instead of pushing out vectors, it's pulling in vectors. So then our flux per unit volume will be negative. The divergence of F is less than 0 for this particular example, where all of the vectors are going into that point. And then I have my third and final example, and that is, what if we have a constant vector field? If you look at any point, in fact, we have just as many vectors going into that point as coming out from the point. So they cancel each other out. And because of that, the divergence of f is equal to 0. So that gives us kind of a geometric picture of what the divergence of f is, which could be understood by the divergence theorem. That's about all I have to say about the divergence theorem, which is all I have to say today. If you have any questions at all about the divergence theorem or about anything else, please send me an email, ask me a question, come by. I'll be happy to help you out. If you have another instructor, please ask your other instructor, and I'm sure your other instructor will also be happy to answer your questions. So whether it's day or morning or night, have a great time, and thank you for watching this video.